We are Madalina Ciortan and Romain Dupuis, and today we are going to present you our work entitled A Framework Using Contrastive Learning for Classification with Noisy Labels. Noisy labels are incorrectly labeled samples which can appear in input datasets, for instance, as a consequence of imperfect web scraping. The objective of our work is to improve the performance of classifiers when trained on datasets having partially incorrect ground truth labels, that is, annotations corrupted by label noise. In a noisy label setting, the overfitting effect of neural networks lowers the performance of classifiers, as they typically memorize the incorrect labels. Several techniques have been proposed to mitigate this loss of performance. One strategy is to employ robust losses, which are functions proven empirically and theoretically to limit the memorization effect. In this work, we analyzed mainly two state-of-the-art robust loss functions, which are the normalized focal loss and reverse cross entropy, depicted in blue, and early learning regularization, in orange, and we contrasted their behavior with that of traditional cross entropy, in green. Contrastive learning is an efficient self-supervised learning technique producing meaningful sample representations using data augmentation. The samples belonging to the same class or instance are clustered together and further away from other classes. One main contribution of our paper is to apply self-supervised contrastive learning to noisy label classification by pre-training the classifiers with such a representation learning phase. The representations learned in an unsupervised way are expected to limit the underlying overfitting. Our method consists of two phases. First, a pre-training phase starts with an unsupervised contrastive learning step and is followed by classification with an arbitrary loss function, such as early learning regularization. The process can stop here, in which case the trained model can be used directly on test data. Alternatively, we can further fine-tune the model. In this case, we use the trained model to predict labels on the train set, which become pseudo-labels, an improved version of the ground truth used in the second fine-tuning phase. The fine-tuning phase starts by using the small loss trick, that is, clustering the training set samples in two groups based on their loss value. The small loss samples are expected to be more correctly labeled than the high loss samples. The clustering is performed with a two components Gaussian mixture model, and we extract W, the probability of correctness, as the membership probability to the small loss cluster. This probability is used in a supervised contrastive training phase, which uses the weighted pseudo-labels as target and pre-trains the model up to the classification head. Next, the classification head is added, and the final classification phase, using the pseudo-labels as targets, trains the final version of the model. Our main contributions consist of demonstrating that the preliminary contrastive pre-training phase increases the robustness of noisy label models, the use of pseudo-labels, and the weighted adaptation of the supervised contrastive loss. The superior accuracy of pseudo-labels compared to the ground truth has been demonstrated by testing on both CIFAR 10 and CIFAR 100 datasets with various types and levels of noise. Our experimental results demonstrate that contrastive pre-training improves the performance of noisy label classifiers, both on CIFAR datasets and on large real-world datasets. We achieved the results comparable with other state-of-the-art methods, which are often more sensitive to hyperparameters. Our experiments also demonstrated that identifying the start of the memorization phase in the absence of clean annotations, which would allow us to perform early stopping, remains an open point. Moreover, the pre-training phase adds an additional computational cost to the overall training time. Thank you for watching.